well, next up we have Chaucer Langbert, and they will be talking to us about the stability and chaos in the habitable zone, climate evolution, and diversity of Earth-like exoplanets. So, Chaucer, take it away.
Thank you, Nara. Hello. So, I'm not going to say that again, but today I'll just be talking about Earth-like exoplanets. So Earth-like planets around sun-like stars in the habitable zone and what behaviors their climates might experience over many billions of years. Now I'm going to pose a question to everyone in the room, so try and think about this for a couple of seconds. If we could actually watch the evolution of 1,000 Earth-like planets, how many do you think would end up like us in terms of warm, stable climate over many billions of years? If you're feeling brave, you can shout out an answer too. I think I saw one. One?
50.
This is kind of a trick question because I don't actually know the answer to this question, but it is really important for guiding future missions that are aiming to look at Earth-like exoplanets. So keep this in the back of your mind. Now, to ground this in exoplanet target surveys coming up, for example, Habitable Worlds Observatory, ideally we should be able to look at about 25 exoplanets or so. But looking at the sample, ideally we'd like to know which ones are like us, which ones are stable and habitable over many billions of years. Those are probably the best places to look for life. Whereas, of course, we're not quite looking for Mars or Venus analogs where we've been thrust in some irreversible, inhospitable state where it's much too warm or cold for life as we know it. And then potentially there are other types of environments as well. So they could be oscillating between cold and warm states, and that would be also a good thing to constrain. But the challenge with doing this sort of work is that there aren't actually models able to do this. This is important because if we want to understand fundamental climate outcomes and guide observations and targeting for future missions, these methods are something that we should care about. Now, Earth has many feedback cycles regulating its climate. Here's only a small handful. The most important ones I want to point out are the ice albedo feedback. So this is a positive or destabilizing feedback on the order of thousands of years timescale. Whereas we also have a very important negative feedback that's called Earth thermostat, which is the carbon silicate cycle. And in this case, it's a stabilizing feedback, but it works on the order of millions of years. I'm pointing these out because these are part of the models I'm going to talk about next. But in order to drive these models, the main question I want to answer now is what general behaviors and stability do we see in climates governed by different feedback cycles? We know Earth has that handful of feedback cycles, but the problem is models currently are very Earth-centric, so they use those feedbacks, but they don't account for different geochemistries on other planets that we may not yet know about. Or they incorporate the biosphere, which we can't necessarily assume that feedbacks are being governed by life on other worlds. So our approach now is to broadly talk about feedbacks without making too many assumptions. So the important things you need to know about this model. So we're tracking mean surface temperature. We're tracking P, which here is the partial pressure of carbon dioxide. I might use that with pressure interchangeably, and for our purposes, that's okay. And then here is fancy jargon for some additional feedback. We don't know exactly what it is. We don't know exactly at the temperatures it operates. But if we randomly sample a whole bunch of these feedbacks, then we can get a bigger picture for Earth-like planets and their behaviors with mechanisms we don't yet know about. So I'm going to have to get into a little bit of math talk so we can better understand figures that have done this work without an additional feedback. So in this case, we have what's called a temperature nullquine. So at any point in this space, in terms of pressure and temperature, you could have an Earth-like planet. However, if you account for the carbon silicate cycle and the ice albedo cycle, what we see is that if you start anywhere in this space, I'll talk about an example trajectory. So let's say you start right here, you're going to get pushed towards this cold temperature. And this is where temperature is stable. So that's why the derivative is 0. That means you only expect partial pressure to change. because it's working on a longer time scale than temperature. So temperature moves very quickly and then will evolve over millions of years as carbon dioxide builds up in the atmosphere through volcanic outgassing. And eventually you should hit a critical threshold where you're able to melt the ice on this world, jump to a warm state, and then slowly relax into what's known as the Earth stable warm state. It's a type of fixed point. And so if you do a whole bunch of different runs for different stellar installations, so how close are you to your star, and the amount of volcanic outgassing you have in relation to weathering, so how much carbon dioxide are you able to put into your atmosphere, we can see that there are broadly two different types of behaviors you can expect. So the first one is either stable glaciated or stable warm state, which is the planet reaches this state, for example, a stable warm state, and it just stays there. It's a great place to be. These are the types of planets we're looking for. But there are certain configurations of outgassing in stellar insolation where you can have something called a limit cycle, where you're actually oscillating between a snowball or cold state and then a warm or hothouse state. I don't know about you, but I probably wouldn't want to live there. So to verify that my model can reproduce this type of behavior, I sent the additional feedback to 0 and saw what could happen. So these are the two feedbacks we're talking about in this particular run, and they work at different temperatures and different timescales. Now, what we're looking at in this middle panel here is that temperature and partial pressure changing over time. So what we see is that temperature grows and then eventually peaks, comes back down. At the same time, carbon dioxide grows over time and eventually drops. And another potentially easier way of looking at this is with this figure here on the right. So we can track temperature and partial pressure over time. And what we see is essentially what the last figure was showing us, which is in a cold state, we build up CO2 over time. We have this rapid transition to a warm state, which eventually cools as CO2 is brought back down into the rocks. And then if we lose too much CO2, we hit a critical threshold where now we reglaciate. And so this is the sort of thing that can actually happen cyclically, which is called a limit cycle. I promise we've done more verification than this, but this is just one example of the behavior we can see. But if we add an additional feedback, now we start seeing some really interesting types of behaviors. So this is called a quasi-periodic behavior. I have a feeling you might be able to guess why, which is we see some fluctuations over 1 billion years, but they're not quite periodic. We see maybe it looks periodic in this segment or this segment, but we also have longer periods of transitioning between warm and cold states. This may not look particularly intuitive. You might not believe me that it's quasi-periodic. So I've come up with kind of a reconstruction of what that might look like. So the axes aren't trivial. Here we have temperature as a function of time. So we see the behavior is kind of constrained between 250 and 300 Kelvin. But now what we've introduced is a lag, and the actual number itself doesn't matter too much. But essentially what you're trying to say is if I have a temperature now and I want to see it at some future point, then I can track maybe some sort of periodic or quasi-periodic behavior. In the very simple case that it was a stable fixed point, you would expect just a point and no movement whatsoever, that the temperature now and temperature in the future wouldn't be changing. But we see here is it's kind of trying to follow a certain path through this space. It's trying to be periodic, but it doesn't quite do that. So you can see with the gray lines that it's tracing that it follows a relatively similar path, but it's not doing it perfectly. And so that's that's a visual way of looking at quasi-periodicity. Now, another potentially more interesting behavior that I was excited about was chaotic behavior. So now we see that the behavior is kind of constrained to live in this temperature and pressure regime, but it's not doing what I showed you before. It's not cycling between warm and cold in a very predictable way. Now it's moving all over the place. And again, a potentially easier way to visualize this is with a 3D attractor. So what this is showing is you can expect to find temperature at certain regions, and you can expect at later times it will probably be close to that temperature, but it's very hard to predict. And so now you see it's following a similar path. It's kind of quasi-periodic, kind of chaotic, but generally harder to predict than the last case. So essentially what I've shown you is from the old case and now to this new model that I have, we can see different behaviors. We can see those fixed points where things are stable. We see limit cycling, but now we see more diverse behaviors. So in this example, I've run 1,000 simulations. And what we see is kind of reminiscent of the other plot I showed you, which is these dark blue points are stable climates. So in this case, these are kind of the cold, stable climates. Out here, these blue are the warm, stable climates. And then kind of in the middle, like we saw that little alleyway of limit cycles. But now there's a couple of oddities happening. So if you add in a little extra flavor with a small feedback, so smaller than the carbonate silicate or ice albedo feedbacks, we can still see interesting behaviors. So we see some yellow points. Those are the quasi-periodic cases. In this case, the chaos was also classified as quasi-periodic because it's kind of a blending of the two. We also see what's called out of bounds behavior, which means the physics of the model does not apply to these cases. The temperature, the pressures got too extreme. And so I had to stop the run and throw at that case. So that would be either Mars-like or Venus-like. In this case, these gray points are Venus-like, where it's too warm. And then for reference, Earth is right here. So we see that Earth's outgassing is almost in equilibrium with the drawdown of CO2 into rock. And we see this is its stellar insolation value. So in sum, this is the first generalized study to look at different feedbacks acting on Earth-like planets in their habitable zones. And this is really key for guiding next generation missions. We were able to verify previous studies with our integrator. We used the HPC, so we were able to do many thousands of runs. And we are able to do many tens of thousands of runs more, which are currently in the process. What we find initially is that an additional feedback actually leads to more diverse behaviors, so quasi-periodic or chaotic behaviors. And hopefully with this data, we're able to directly link to exoplanet missions by populating exoplanet demographics and providing priors and stats talk, Bayesian priors for hypothesis testing of these worlds. Yeah, that's all I have. Happy to take any questions.
Take questions in the room and also online.
I'm wondering, does your model allow for the PCO2 to feed back into the planetary albedo? On the slide where you had the expression, there was
yes.
an alpha naught that I'm thinking maybe was like an albedo flare.
Yes, so that alpha T, that's albedo as a function of temperature. So if you're in the glaciated state, you have a higher albedo versus the warm state. So it's kind of averaging over the entire surface.
Okay, but it doesn't depend on PCO2
No,
directly.
just temperature. Yeah.
Keep the input from the star fixed.
Yeah, that's something I've played with a little bit, which is if you start the star at about 70% brightness and ramp it up, essentially what you're doing, it's similar to this, because the star ramps up so slowly, eventually what you would get is, for example, an Earth-like case where you start with 70% brightness and move it up, you would still get the same result. If you added in noise, that's something I've thought about looking into, because the rate of change of stellar insolation can actually cause some really interesting artifacts. But generally, we don't expect it to massively change results. So I guess it depends on what stage of evolution that planet is in, then you can input its stellar insolation value, and it shouldn't matter too much.
Seemed like it should be straightforward to just incorporate it in some way.
Yeah.
So I was kind of curious why not.
I think mostly this was to partially verify the results of the other paper where they kept it fixed. But when I incorporate potentially larger amplitude feedbacks that are similar to, say, the carbon silicate cycle, that's something I'm planning on doing.
So why the rightmost boundary is so close to the sun?
Yes. Yeah.
You have a lot of unclassified points in this plot. I'm just wondering what that means and what is between that and out of bounds.
That's fair. So unclassified, this classifier I have is still a work in progress, but unclassified just means there weren't enough data points from the actual integration. So either that means there was some weird numerical precision error or something like that that caused the run to crash, or some similar thing. These are definitely points to look into.
That's really interesting. And I guess my question is limit cycle behavior a bad thing? Earth goes through snowball Earth and hothouse climates. Early Mars climate seems to have oscillated between, wetter and drier periods.
Yeah, I guess the answer depends on who you ask. We know that, for example, there have been snowball Earth periods in our past, which this model approximates it as the world as a full snowball, but that might not be the case. There might be some low latitude water bands or other things where life could still exist in an ocean even with the snowball. It's probably not great, but it wouldn't totally rule out life, I don't think.
Questions in the room or online?
Just to bring it back to the original, your first slide or two, where you were saying how these results would inform future missions, calculations. Can you say a bit about that connection again?
Sure, yeah. So essentially the goal is from many simulations, we can start to predict if there are Earth-like planets, but maybe with different types of feedbacks than we have. We should see a certain distribution. And so from that, we can say, if we're able to look at 25 Earth-sized exoplanets, how many do we expect to have limit cycle behavior or chaotic behavior, and what are some of the observables we could see? So I know Rahul talked about volcanism a little bit. That one might be difficult, but there are different features we might look out for. So maybe albedo. So if we see really high albedo in many planets, it might be clouds, but it could also be full ice cover. So it depends partially on the actual mission that's looking for it, but I think all of the work being done on observables for these sorts of planets will better inform.
If a planet is tidally locked, what complication does that throw into your modeling?
A lot. I think partially this model is assuming an Earth-like planet in the habitable zone of a sun-like star, which means generally we don't expect as much tidal locking. I think that sort of regime is closer to the star and potentially too warm. But if we did happen to have a case with tidal locking, then I'm not sure this would be a valid way of talking about it, because we're assuming, for example, ice cover that's globally average and temperatures that are globally average, and that starts to break down. Yeah.
Do you plan to couple this model to other stellar types, like an M-dwarf?
That would be a really interesting question. It's not something I've thought about as of yet, but it's something that's definitely possible, playing with the different stellar insolation values. But it is assuming kind of an Earth-like scenario in the sense that CO2 isn't being lost too quickly, so it's not it's receiving a crazy amount of instant flux. But that would be a really interesting fact to take.
Okay, if there are no more questions, let's thank our speaker.